Hello, welcome to AB Video 3.7b Part 2, the end, finally, of optimization problems. Number 42, 20 feet of wire is to be used to form two figures. In each of the following cases, how much wire should be used for each figure so that the total enclosed area is a max? So I'm doing number A. So we have 20 feet. We're splitting it into two pieces. I'm calling the pieces X and 20 minus X. And we're going to form, with one of these pieces, we're going to form an equilateral triangle, and with the other piece, we're going to form a square, and we want the total enclosed area to be a maximum. All right, so if I take the piece that's side length X and I fold it into an equilateral triangle, obviously each side will measure X over 3. If I take the piece that measures 20 minus X and fold it into a square, then each side of the square will be 20 minus X divided by 4. I want to maximize the total area, which means I want to maximize A being equal to the area of the triangle plus the area of the square. Now, the area of an equilateral triangle, don't know if you know that formula, but if you don't, which I don't, of course, if I drop the altitude, it's also the angle bisector, so I've created a 30, 60, 90. It's also the median, so this x over 3 gets divided into two congruent parts, so that's x over 6. And then, of course, this is 2k, this is k, this is k root 3. So the height is actually x root 3 over 6. The area of the big triangle is 1/2 its base, which is x over 3, times the height, which is x root 3 over 6. The area of the square, of course, is the length of the side squared. And therefore, here is your formula in A and X. What is your domain? Well, X obviously has to be positive, and X is sure not going to be any less than 20. Now, I'm going to put equals here because, as it turns out, this would be the novel case where it turns out you're going to use all of it for one of the figures. So we're going to find our derivative, etc., blah, blah, blah. Or if you're using a calculator, you could just graph the function, and you'll see that the maximum point on that interval from 0 to 20 happens to be when x is 0. So the idea is to not make a triangle at all and to use the whole 20 inches to make your square. Okay? Critical number will produce a min, not a max. I'm looking at the graph here if you actually graphed it. Okay, this is the last and most difficult of the application problems, optimization problems. An offshore oil well is 2 kilometers off the coast. The refinery is 4 kilometers down the coast. Laying pipe in the ocean is twice as expensive as on land. What path should the pipe follow in order to minimize the cost? You too might be an engineer one day working for the oil companies and having to figure this out. So here's our nice little picture. So here's the shore, here's the water with the sailboat and the little fishies and the waves, okay? Here's our oil well. It's out here in the sea. It is 2 kilometers from shore, which would be a perpendicular shortest distance to shore. And the refinery is down here, 4 kilometers away from that point, directly opposite the oil well. So there's 3 choices. You could lay your pipe directly towards the shore and then directly along the shore. You could lay your pipe directly from the oil well directly to the refinery. That would be all under the water. That would probably be very expensive. Or you could do a combination of both, part of it under the water, the rest on land. So we're going to assume it could be both, and then if it ends up being one of the other 2 possibilities, you'll find that out. Okay, so we know this is 2. If I call this length x, since this is 4 kilometers, this length is 4 minus x. I'm going to call this length s. That's the length of pipe under the water, and the length of the pipe on land is 4 minus x. Once I have that this is 2 and this is x and this is s, I actually have the Pythagorean theorem, and that might come in handy a little later. If you let k be the price in dollars per kilometer to lay the pipe on land, then to lay it in the ocean, the cost would be 2k dollars per kilometer because it's twice as expensive. Now, we want to minimize the cost, so we want to minimize the cost of laying the pipe in the sea plus laying the pipe on land. The length of the cost The length of the pipe in the sea is S, which is the square root of 4 plus x squared. The cost is 2k dollars per kilometer. The length in kilometer on land of the pipe that you would put on land would be 4 minus x kilometers, and its cost is k dollars per kilometer. The domain x would have to be between 0 and 4. Okay, x could be 0, it could be 4, it could be one of the extreme values. You find your critical numbers, and it turns out it does happen in between. It happens when x is 2 root 3. That's the point. That'll be the cheapest point, is to run it under the water until that point where x equals 2 root 3. So this length being 4, this is 2 root 3 right here. So working backwards from there, and then the rest